Hi, I'm Thomas Smith, and this is my UROS project on the angle conditions in branch groups, which was supervised by Dr. Anita Tillerson. So we'll just get straight into it. So a quick overview. The project sought to determine two things. Firstly, a generalisation of Bludov's example of a non-angle branch group made up of the Reith product of the cyclic group of order 4 with the Grigor group to an example with the twisted twin. And secondly, an attempt to generalise Bartholdi's result that the Grigor group is not angle, and we're generalising this to the twisted twin. So this is obviously a UROS project on group theory. So what actually is group theory? So group theory originates from the ancient Greek studies of symmetries acting upon polygons and polyhedra. So basically how the symmetries of a shape interact with each other, of which the set of is now known as the symmetry group of isomeries of a shape. In the 19th century, Galois studied the permutation group of a root of an equation, and he found that the structure of the group determined the solvability of the equation. So, and from this, Galois created his own branch of mathematics, which is actually dedicated to this study of roots of equations. It's now known as Galois theory. Then in the late 19th century, Cayley gave the first definition of an abstract group, which was later developed into the modern definition by Weber. So Weber developed the definition to a set with a binary operation which follows 4 fundamental axioms. These are closure, associativity, inverse and identity. It's not important actually what they are at this point, just as long as you kind of get that a group is a set of objects which interact with each other in a certain way. So this project actually focused on specific groups known as branch groups, in particular the Grigor group and the twisted twin of the Grigor group. So what is the actual motivation for studying branch groups, such as the Grigor group? So a strong motivation is Burnsides problem, which is stated as follows. Let G be a finitely generated torsion group. Is G necessarily finite? So it sounds quite complex, but basically what this means is, does there exist a group with infinitely many things in it which can be generated by a finite number of elements, and where each element is torsion? Which means to have a finite size with respect to the group. For a while this was an open question until Golod and Shafarevich showed that for each prime number p there exists a corresponding infinite p group on 3 generators. However, their proposition lacked any direct construction of any such groups, which by this time were being referred to as Burnside groups. So groups that are well, we'll come to that in a minute, but in 1980, Grigor constructed the first explicit example of a Burnside group, known as the Grigor group, and this was considered a major breakthrough in pure mathematics due to the level of renown that the Burnside problem has achieved. So a Burnside group is actually a group that's infinite, finitely generated, and torsion. So obviously the answer to Burnside's problem was that G doesn't necessarily need to be finite if it's finitely generated and torsion. So, branch groups. What are branch groups? Informally, a branch group is a subgroup of the automorphism group of a spherically homogeneous rooted tree that has similar properties of the automorphism group of the tree itself. But the formal definition is actually really complex, but as long as we understand that a branch group is a set of automorphisms or symmetries of the binary rooted tree, with the operation being combinations of symmetries. And the binary rooted tree, I'll draw it here at the top, actually looks, so it starts off with a root, and then it's binary, so each vertex, sorry this is going to be awful, each vertex has 2 vertices incident to it, hence binary, so this one would have 4, and so on, and it's infinite, so that goes on forever. And each row is called the level, so this is the first level, the 4 vertices here will be the second level, the 8 here will be the third, and so on. So anyway, branch groups have tree-like subgroup structure and act transitively on every level of the tree, which means that at every level of the tree there is exactly 1 orbit produced under the action. And the theory of branch groups is relatively new and it's still in its infancy, so there's a lot of good research coming from this area of mathematics at the minute. So first let's discuss the Grigor Group. So in a paper titled On the Burnsides Problem, Grigor Group gave the first construction of a branch group that was infinite, torsion and finitely generated, i.e. a Burnside group, and this became known as the Grigor Group, or some people also call it the first construction. It is a 3-generated 2 group that acts on the binary rooted tree, so it's generated by 3 automorphisms of the binary rooted tree. So these are, if we say alpha is the automorphism or symmetry that permutes the 2 subtrees incident to the root, then we have beta is equal to alpha gamma, gamma is equal to alpha delta, and delta is equal to 1 beta. And we say that the Grigor group is the group generated by alpha, beta, gamma, and delta. So which means that every element of the Grigor group is going to be words in the letters alpha, beta, gamma, delta. So it could be, for example, alpha, beta, beta, gamma, alpha, delta, or there's infinitely many combinations. So even now, people are still using the Grigor group to answer and dispute many important open problems in group theory. Next, we're going to discuss quickly the Engel problem. So let G be an arbitrary group, and let X and Y be elements of G. The left Engel commutator, which we denote as X, N, Y, is defined as like continuously taking the commutator n times. So if you're unfamiliar with the concept of a commutator, it can be sort of thought of as like as the difference between 2 elements, so in this case the difference between element X and element Y. One can also view it in terms of the group operation, so it shows how commutative the operation is or isn't. A group G is Engel if all of its elements are both left and right angle. So as we said, left angle was when we take the commutator from the left, right angle would be just the reverse, taking the commutator from the Y. From the right, but from the Y. The main problem within Engel theory is classifying groups up to either being Engel or not Engel. And we'll see a couple examples of groups that are not Engel and justifications for why this is the case. So basically the Engel problem is what is the most efficient way of determining if a certain group or family of groups is Engel or not. And it's not currently known what this is, as it's quite a modern area of study. So now we'll discuss the twisted twin of the Grigor group, which is the other branch group that's that the majority of the research is about. So a few years after the Grigor group was discovered, probably about 25 years, Bartholdi and Siegenthaler discovered a twisted version of the Grigor group. So it's known as twisted due to a slight difference in the automorphisms that generate the group. So if we remember, the second directed automorphism in the generating set of the Grigor group, which was beta, was beta equals alpha gamma. Now if we look at the automorphisms that generate the twisted twin, we can see that B, which replaces beta, is actually C alpha rather than alpha C. And obviously we've relabeled the letters as the letters that we know. So the twisted twin is generated by A, B, C and D. So this group isn't actually isomorphic to the Grigor group, and it has very different structure to the Grigor group. Quite a similar structure, but there are a lot of similarities and differences. So in short, the fact that they're not isomorphic means that the 2 groups aren't the same group. They're actually different, which doesn't sound like much of a point, but it is quite unexpected to the group theorist, as usually with groups of such a similar nature, one would expect them to be structurally identical, which is what isomorphic means, but it's actually been shown that they're not. So now we'll look at just a bit of a comparison between the 2 groups. So as we've seen, the difference between the Grigor group and its twisted twin seem very minimal. It's just the difference between B and beta. However, this small twist has a huge impact on the difference between the 2 groups. For example, in the research that we conducted, we found that the computations with the twisted twin are substantially more complex than that with the Grigor group. And we determined that this is because the automorphisms that generate the Grigor group commute, whereas in the twisted twin they don't. So what it means for something to commute is that for elements, we can move elements around when we're doing computations. So for example, an easy example could be when we multiply the numbers that we all know and love, 1, 2, 3, 4, 5, so on, we can swap them around. So we know that 7 times 3 is equal to 3 times 7, which means that they commute. However, when we subtract numbers, we can't do this because obviously 7 minus 3 is not equal to 3 minus 7. So that operation is not commutative. So the group theorist would say that the numbers, or we call them the real numbers with multiplication, is a commutative group because we can swap them around. And we call this an abelian group. And the numbers with subtraction isn't commutative, and it actually isn't a group because if one looks, it doesn't obey the 4 axioms of group theory. A really important difference between the two groups is that the Grigor group has the congruent subgroup property, whereas the twisted twin does not. So the CSP, congruent subgroup property, basically tells us about the projections of a group, so it tells us about what its quotient groups look like. And these groups are fundamental. They're a fundamental group to group theory, and they're of huge importance. And I'm not going to talk about them here because it takes quite a lot of previous understanding, but they're really important. And because the Grigor group has this congruent subgroup property, we can talk about its quotients. We know what its quotient groups look like, whereas with the twisted twin, we don't. So the aim of the project, just to recap in before we go into the main results. So the main goal of this project was to assess the Engel conditions within the twisted twin of the Grigor group by making comparisons with the Engel conditions in the Grigor group. The main findings of the report were split up into 2 generalizations of 2 different examples. The first being an example of, the first was an example of Bludov, I've accidentally written Bartholdi, which demonstrated using the Grigor group that the set of left angle elements is not in general always a subgroup. And the second example, which actually was by Bartholdi, showed that the Grigor group is not angle. So first we'll go over the example of Bludov. So in a lecture by Bludov, quite a few years ago now, he gave an example how the set of left angle elements is not a subgroup in general. So this was achieved by taking the Reith product of the cyclic group of order 4 with the Grigor group and finding an element such that when we continuously take the commutator with any element, we will never obtain the identity element. If we did obtain the identity element, going back to the definition of an Engel commutator, then that element that we chose would be an Engel element. But because we found one element that isn't Engel, we can say that the group itself isn't Engel because every element would need to be Engel in order for the group to be Engel. So in maths language, we let a subgroup K, which is equal to the group generated by G, such that G is of order 4. So therefore K is a cyclic group of order 4. Now we define G as the Reith product of this cyclic group of order 4 with the Grigor group, and choose some element in this group, which would be a quadruple, which is kind of like a coordinate, but with 4 entries, such that we can show that the Engel commutator is not the identity. So in order to do this, we manually perform the calculations for each commutator and produce a loop, which gives us the original element H that we chose originally. And in order to, Bludov's choice for H was given by the quadruple 1, beta alpha, alpha gamma, and delta. And it can be shown that when we reach H16, so the 16th commutator, we obtain H again. So this is a loop. And it demonstrates that the Reith product is not Engel. The reason why, just quickly getting a loop demonstrates that it's not Engel is because if we start off with H and we take the commutator, we're going to get a new quadruple. So we're going to keep taking commutators, getting a new quadruple, kind of putting in 2 of these quadruples, it spits out a new one. So when we take it a 16th time, we're going to get a new quadruple. And if this is H, which is the original element we started with, we're just going to go in a cycle then, because H17 would be the same as H2, H18 would be the same as H3, and by the time we reach H32, we're going to get H again. So we're never going to get the trivial element, basically. So how would one generalise this example to the twisted twin? So as before, consider the cyclic group of order 4 and define the Reith product as A as the Reith of K and the twisted twin of the Grigor Group. And again, one seeks to show that there exists a quadruple such that the angle commutator is not equal to 1, or the identity. However, we found that in using the same choice as Bludov, or a similar choice to Bludov, as h equals 1, a, b, c, a, d, actually gives the trivial element in this setting, whereas for him it worked quite nicely. So this means that h actually is a left angle element in this case, so we'd need to find a different choice for h. So when we were generalising this example, we found that there are some ways in which one could simplify the choice for the element h. So for example, we want to choose a quadruple where we won't lose any generators when it comes to continuously taking the commutator with g. And this is because once we lose a generator, we'll never get it back. And we actually demonstrated a proof for this in the report. I won't include it here just because it's quite lengthy. But a good way to choose a quadruple that would not lose any generators when we continuously take the commutator is to choose a quadruple with one component not in the first level stabiliser. And this ensures that we need to take the commutator 4 times before we have all components in the first level stabiliser, meaning that we can take the first level projection and then carry on with the calculation. So this whole sounds a bit complex, but all one needs to understand is that what this does is it reduces the choices for an element h, which are more likely to provide us with a new loop. And the reasoning behind why it increases the chances is to do with the fact that we have to wait until we have taken the commutator 4 times each time we want to project into the first level of the tree, so that we can work with smaller words which are made up of a's and b's, etc. It just makes the odds a bit greater, really. We actually never found a choice for h, and we did try quite a few choices, but after we applied this tactic, we did find a choice where we could take the commutator, I think it ended up being 76 times, and we didn't lose any generators, which gives us a really, really strong hope and belief that the example can be generalised, maybe with another few computations. For all we know, it could be 1,000 times, but this is open for research, I guess. So next we discussed Bartholdi's results. So in 2012, Bartholdi demonstrated that the Grigor group is not Engel. So the natural way to show this is that a group is not Engel is to take some element in the group, and we show that for any element h, we have that the Engel commutator is not the identity. So again here, we've taken the commutator n times. It's just a bit of an abusive notation, but that's what it means. So Bartholdi's proof demonstrates that all elements not of order 2 are Engel. So this shows that the set of left angle elements of the Grigor group consists exactly of the involutions, which are the automorphisms of order 2, and is thus not a subgroup. And therefore, the Grigor group is not Engel. So the proof is actually very difficult to follow, even for a very strong mathematician, but in short, Bartholdi fixes a quadruple as given below. I'm not going to try and read that out, but this is the element h that he chooses. And then Bartholdi showed that using gap calculations, that if we consider a vertex of the tree, u equals 0, 0, 0, 0, 0, 1, the element a9i fixes u, and it's such that the section of a9i is equivalent to a0i. This might mean nothing at this point, but it's very important later on. And also gap is it's a new computer coding software that allows you to make quite difficult computations inside groups with ease. I personally don't know how to use it, which was a massive drawback, as there was a lot we could have gained from using it. It's something I really want to look into using in the future. He uses a number of previously formulated results to show that the Engel commutator of G with H is not equivalent to the identity, which tells us that the Grigor group is not Engel. I'm not going to go into the proof here because it is, again, really lengthy, but it is featured in the report. A full generalisation of Bartholdi's proof could not be obtained, since I lack, as said, an understanding of the gap computer software to finish off the proof. However, the necessary tools have been set up to determine a full generalisation, which we'll go through now on the last. So this is what was found. So as with Bartolli's proof, we'll do the same. Consider a cyclic subgroup H such that H is not an involution. Now, since G is a 2 group, every element has order of a power of 2, and therefore there exists F, which is minimal in the natural numbers, such that H to the 2 to the F equals 1. So the first thing we generalised was that if n is a natural number, the action of H in the subgroup H at the nth level has an orbit v1 through v2 to the f, which has length 2 to the f. Proof, again, is included in the report. And secondly, let G and H be elements of the automorphism of the binary rooted tree, and let G be an element in the nth level stabilizer. Then for all u in that level of the tree, if v is equal to the inverse of hu, we have the following, which again I'm not going to try and read out, but again the proof is in the report. So to conclude, unfortunately the paper did not fully achieve what it set out to show, so there's an obvious opening for future research in this area. Me and my supervisor are actually still planning to work on this after the UROS project to see if we can do those extra computations to get the first example generalised and to learn the computer software so that we can finish off the second proof. And I am looking to do this maybe as part of my master's thesis this year. However, even though a generalisation of Bartolli's result could not be determined, a number of important observations have been pointed out and mathematically formalised, which will benefit future researchers who wish to determine the same result we wish to demonstrate here. So yeah, thank you so much for listening, and I hope you enjoyed it, and yeah, that's the end of this presentation. Thank you very much.